In our last lecture, we talked about the linearization process. When applied to a nonlinear system at an equilibrium point of a nonlinear system, gave as an approximation of the nonlinear system a linear system. Okay, and it's a very useful thing to be able to obtain as an approximation even a linear system from a nonlinear system, because in general we don't know how to obtain the solutions of the nonlinear systems, but we have many powerful tools to study an LTI system, a linear system. Therefore, we can apply those tools to that linearization, to that linear system, and obtain very useful ideas regarding the local behavior of the actual nonlinear system. So we figured out the procedure last time, and in this lecture we begin with an example where we apply that process to a nonlinear simple system. Consider the following second order system. Given as a second order scalar differential equation, y double dot equals minus y plus y cubed plus u. Okay. This can be considered as a nonlinear mass spring system. Okay. Without the y cubed term, you would have y double dot plus y equals u. Okay, so that's the universal equation for the harmonic oscillator. And now we have, in addition to that linear model, we have this y cubed term, representing some nonlinear effect in our system. Now for this system, we're asked to do the following. First, we're going to obtain another representation of this system, but equivalent representation of this system that's more suitable for linearization. Okay, and that representation we called it state space representation. Okay, so first we're going to obtain its state space representation. Okay, and then using that state space representation, we will obtain its equilibrium points, if it has any. Okay, find the equilibrium point or points for that system for the case where, let's say, force applied on the system is 0, for u equals 0. And then for one of those equilibrium points, once we have found them, we're going to apply the linearization method. But let's first go through parts A and B. Okay, here is the solution. Now, for such a system, it's usually best to choose the state. First of all, notice that it's second order. Okay, therefore, the state space representation will have a state that has two individual state variables. Okay, so we have to choose x1 and x2, and then by having chosen x1 and x2, we will obtain the state space representation, namely x that equals f of xu and y equals g of xu. Okay, so usually the obvious choice for such simple systems is choosing first state variable as output, or in this case, let's say the position, and the second output, second state variable can be chosen as the velocity. Okay, in other words, y and y dot will be our state variables. Let's call y position x1, and let's call the velocity, namely y dot, as our second state variable x2. Okay. Once we have x1 and x2, we can easily obtain the state space representation x that equals f of xu and y equals g of xu. So this is our f of xu, and here we're talking about, since we have two state variables, the system is second order, and here therefore we're talking about a vector where each entry is a function of the state and the input. Okay, so for the first entry we look at x1 dot equation. Okay, so what's x1 dot? X1 dot is y dot, and y dot is x2. Therefore, the first entry is a very simple function, x2. For the second entry, which we call f of 2, we look at the time derivative of the second state variable, which is x2. x2 dot is y dot dot. Okay, so y double dot and y double dot is here, which is minus x1 plus x1 cube plus u. Minus x1 plus x1 cube plus u. Okay, so this is our right-hand side for this state space representation. As for the output, it directly equals the first state variable. Therefore, this is our, according to our earlier notation, general notation, this is the function g. G of x u. So this is a common. Okay, now we have the state space representation. X that equals f of xu and y, the output equals g of xu. Now we can move on to part B and figure out the equilibrium points. That's what we do, is we set u to 0 because we've given that. Then once u set to 0, what we have is f of x comma 0. So our system is x that equals f of x comma 0, and the equilibrium points for that system is such that at those points the velocity is 0. Okay, velocity x that equals 0. So x that equals 0 means that if you start at that point, because velocity is 0 at that point, you move nowhere. And if you move nowhere, you stay there forever. That's why it's called an equilibrium point. Okay. So let's figure out those equilibrium points. Okay, by definition, at equilibrium, the right-hand side is 0. Okay. f of xu equals 0. So this would imply, for our case, that x2 minus x1 plus x1 cube plus u equals the 0 vector. Okay. So we're told that we should take the input to the system to be 0, and then under that condition, let's figure out the equilibrium states. So there's nothing to solve for x2 at equilibrium, it directly equals 0. Okay. So therefore we have at equilibrium x2 must be 0, and minus x1 plus x1 cube should also be 0. Okay. And we have minus x1 plus x1 cube equals 0. And this polynomial of order 3 has 3 real roots. Okay, so we're only interested in the real roots. Therefore, that means we have 3 different equilibria. Okay. So solving this implies that x1 is either 0 or it's plus 1 or minus 1. Okay. Therefore, 3 equilibrium points are obtained for the system under the condition that we set the input to 0. So the equilibrium points we call x bar. So x bar belongs to this side. Okay. 0, 0 is an equilibrium point. Okay. Okay. Well, first of all the equilibrium points must have x2 equals 0. Therefore, we have zeros here. And as for x1, it could be 0 or 1 or minus 1. Okay. 1 or minus 1. All those 3 points are equilibrium points. Okay. Now, let's linearize our system at one of those equilibrium points. So that's our part C. Linearize the system at the equilibrium point x bar u bar equals 1, 0, and 0. Okay? So we're linearizing the system around that equilibrium point 1, 0. So that means at that point you obtain a linear system, and that linear system is an approximation of the nonlinear system. Okay? Okay, for that we need the ABCD matrices. Okay? The matrices that appear in our LPI system, in our linearization. And those matrices we obtain through the following partial differentiation. Okay. We have, we have to compute this matrix, which is delta x1, delta x2, delta x1, and delta x2. Okay. Now this equals what? Okay. This is our f of xu. So this thing here is f1, and this thing here is f2. Okay. Therefore, partial derivative of f1 with respect to x1 is, well, x1 does not appear in f1, therefore this entry is 0 at all points. And then we have this term, partial derivative of f1 with respect to x2. f1 is x2, therefore when you take the partial derivative you obtain 1. So this entry therefore is 1. Okay, we move to the second row. Partial derivative of f2 with respect to x1. This is our f2. If you take the partial derivative with respect to x1, we have minus 1 plus 3x1 squared. Minus 1 plus 3x1 squared. And finally, this entry is partial derivative of this term with respect to x2. x2 do not explicitly appear in that expression. That means this entry is 0. Okay. So this is the general expression of f partial derivative of f with respect to x. Okay, and now we're going to evaluate this at this particular equilibrium point in order to obtain the A matrix. Okay, so that's our partial derivative of f with respect to x. Quickly, let's also write down partial derivative of f with respect to the input. Okay, so this is derivative of partial derivative of f1 with respect to u and partial derivative of f2 with respect to u, and you see that it's simply 0 and 1. Okay, and then partial derivative of g with respect to x is 1, 0. Partial g with respect to x1, partial g with respect to x2, and since g is simply x1, okay, our first state variable, it's in a sense it's already in linear form, and this is the matrix that appears 1, 0. And finally, since the output does not explicitly depend on the input, because y equals or g equals x1, the D matrix, excuse me, eventually it will be our D matrix, but partial derivative of g with respect to u is 0. Okay. Now this is our A matrix, B matrix, C matrix, and D matrix. evaluated at the equilibrium point. Okay, well, we have to evaluate those expressions at the equilibrium point in order to obtain the corresponding ABCD matrices for our LTI approximation. So that means the A matrix equals, okay, take this and evaluate at 1, 0, 0, okay. That is, plug in wherever you see x1, 1, wherever you see x2, 0, and wherever you see u, 0, okay. We have that only x1 appearing there, and if you plug in x1 equals 1, you have minus 1 plus 3, that's 2. So 0, 1, 2, 0 is the A matrix of our approximation or generalization. B, well, it's the same at all equilibrium points for B01 and same for other matrices. Okay. Therefore, the linearization is psi dot equals A psi plus BU and W equals C psi. Okay, so this is D, and A, B, C, D are given here. Well, B is 0, we can write it here. Okay. The linearization at the equilibrium point 1, 0 and U bar equals 0. So this means what in terms of the original system? So the original system was x that equals f of xu. If you start this system at, let's say, x0, okay, and apply to it u of t, you obtain a solution, or you expect to obtain a solution. Let's call that solution x of t. Okay. And then what you do is, with the linearization, you start the linear system from, okay, x0 minus x bar. Okay. So that's the initial condition for your system. This is whatever the initial condition of your original system is. X bar is where we perform the linearization, which is 0.10. So this minus that, it gives you a vector. Okay, in R2, and that vector is where you start your system from. And so that's the initial condition. What's the input that you run the system with? Here you have u of t, and then to the linear system you apply the input u of t minus u bar. But since u bar is 0, you're applying the same input to your linear model. Okay, and then your linear model will give you a psi of t. Okay, and the relation of this psi of t to x of t is the following: x of t, okay, equals approximately x bar plus psi of t. Okay, and this approximation is good as long as x and u remains close to the point where you perform the linearization, x bar u bar a. Okay. Now let's close this case with a question, and then we will move on to a new thing. New question that we want to ask ourselves is the following. So we covered in detail the process of linearization for continuous time system. Note that there are also discrete time systems, and they're also of interest. And it's therefore important to be able to know how to linearize them around equilibrium points too. So therefore, this question is important, but it's very easy to answer. So I'll leave it as an exercise. Okay. How about the discrete time case? is x plus the value of the state at the next time instant is given by this map. Let's say f of xu and y equals g of xu. Okay. So how do you apply linearization? That point, and now for continuous time when you apply linearization, the result is a linear system only if you linearize system at an equilibrium point. Therefore we expect the same thing for the discrete time case, but of course now we have to be careful about what we mean by an equilibrium point. So this happens to be an important question to answer, but it is a very easy answer. How to define equilibrium point, okay, for a discrete time system. For a continuous time system, x equals f of xu, equilibrium point was simply this equals 0. Okay? How about the discrete time case? That's something good to think about. Now, in the second part of the lecture, we will talk about something new, and then we will be continuing talking about that in our following lectures. And the thing that we want to discuss now is the following. Okay. So we have seen so far that a linear system can be represented by the so-called state space representation, okay, where we have A, B, C and D matrices, okay, like here. Now we also know that there are other representations, and one of the most widely used other representations is the transfer function, which is peculiar to linear systems only, because we don't have such a thing for nonlinear systems in general. Okay. Now since the state space representation and the transfer function, they are two different representations, but they're representations of, let's say, the same system. Clearly, there must be a relation, a precise relation between that pair. Okay? Now we will talk about that relation. That is, given, or more precisely speaking, given one of the representations, how we can obtain the other representation. So transition between different representations of linear time invariant systems. Okay. In particular, we will be interested in the transition from the state space representation to transfer function and the reverse direction. Okay, now let's start with the easy part, which is given the state space representation, let's obtain the transfer function, the corresponding transfer function that represents the same system. So state space representation to transfer function representation. Okay, so this is supposed state space representation of our system. X equals ax plus u, y equals cx plus d. A, B, C, D, they are constant matrices. To go to the transfer function, what we do is we first go to the complex frequency domain, or in other words, Laplace domain by Laplace transform. Okay. So let's take the Laplace transforms of both sides, both right and left. And if you do that, here we have x dot. Okay. The Laplace transform of a function's derivative is the Laplace transform of that function minus times s, and then minus the initial condition. So in other words, we have s times x of s minus the initial condition for x. If the initial condition is 0, then the Laplace transform of x dot directly equals S times the Laplace transform of x. And that equals the Laplace transform of this. A and B are constant matrices. X of t and u of t, they are variables. Therefore, due to the linearity property of Laplace transform, we can easily write the right-hand side as A times x of s plus b times capital U of s. Laplace transform of the state and Laplace transform of the input. Doing the same thing here, we immediately obtain y of s equals c x of s plus d U of s. Okay, so let's call this equations 1 and 2. Okay. And now, by definition, transfer function is matrix in general with entries that are rational functions of S, such that that matrix transforms the input to the output under the assumption that the initial conditions are zero. In other words, the transfer function matrix is such that y of s equals, let's call it g of s times u of s. And the question is, what's g of s, the transfer function matrix, for a state space, for a linear system whose state space representation is this? Or even more precisely, we want to obtain the transfer function matrix in terms of our parameters a, b, c, and d. Okay, so let's start from equation 1. Now, equation 1 implies that s x of s minus a x of s equals lowercase x is 0. This is the time domain signal. Its value at t equals 0 plus b times u of s. So what we did, we collected the x terms on one side and let all the other terms appear on the other side. Then we can write this as si minus a times x of s equals x0 plus b times u of s, and then multiply both sides with the inverse of this matrix si minus a. We can write x of s as si minus a inverse times x0 plus si minus a inverse times b times u of s. Okay, and then since what we want is a relation between the output and the input, what we do is, next, we plug this expression into equation 2, into where we see x of s. So let's do that. Let's call this equation 3. And then we're going to combine equation 2 and equation 3. We will assume that the initial condition is 0, and then that will give us the transfer function. Equations 2 and 3 yield the following: y of s equals c times si minus a inverse x0 plus c times si minus a inverse d plus d u of s. Okay, and this object that appeared here is what we call the transfer function of the system. So by definition, this is our transfer function. Usually, transfer functions are shown by g or h, but clearly it doesn't matter. Whether you choose to show it with. So clearly, when initial condition is 0, your system, that is x0 equals 0, that is all the capacitor voltages are at 0, all the initial conductor currents are 0 for an LTI circuit, then we have y of s equals g of s times u of s, meaning that if the initial conditions are 0, if you know the transfer function of the system, you can figure out the output for a given input by multiplying the Laplace transform of the input with the transfer function, and then take the inverse Laplace transform of that product, and that will give you y of t. That will be the zero state response, because we take the initial conditions of our system to be 0. Okay. So let's summarize what we have figured out, which was obtaining a relation for the transfer function in terms of the state space representation parameters, namely the matrices A, B, C. So G of S equals C times Si minus A inverse times B plus D is called the transfer function, and in general it's a matrix. It's a scalar only when the system has both the input and the output scalar variables. Okay, so if such systems are called single input, single output systems, and when your system is single input, single output, then transfer function is just a scalar function. Okay, in more general cases, it's a matrix. Okay, and how many columns and how many rows that matrix has depends on how many inputs and outputs you have. Okay, so this is called the transfer function of the linear system, or the linear time invariant system. X that equals ax plus du, and y equals cx plus d. Okay, now let's notice some properties of the transfer function, and then we will move on to the other direction, from transfer function to SS. G of S, the transfer function, is an m by k matrix. Okay. So what's n and k? N is a number of individual output variables that we have, the number of outputs. And k is the individual number of individual inputs that you have in the system, number of inputs. Okay. What else? The entries of G of S. Let's call them G, I, J. I throw jth column entry of G of S has the following form. Some polynomial of S dividing some other polynomial of S. Okay? And the degree of this polynomial is never smaller than the degree of the numerator polynomial. Q, I, J, and P, I, J are polynomials in S with degree of the numerator never larger than the degree of the denominator for each entry. Okay, that is, all entries of our transfer function matrix, all GIJs, okay, are so-called proper rational functions. Okay. If degree of Qij is strictly smaller than degree of the numerator Pij, then the corresponding entry Gij is called strictly proper. Okay. It's called strictly proper. Okay. And if all the entries of our transfer function matrix are strictly proper, then we call that our transfer function matrix itself is a strictly proper function. If all GIJs, all the entries of our transfer function are strictly proper, then G of S itself is called strictly proper transfer function. Okay. Well, for a single input, single output system, this is a matrix of 1 by 1, therefore itself is a scalar, and we're talking about a single entry, and that entry directly equals transfer function itself. Okay, in our next lecture, we'll be talking about the reverse direction, meaning that given G of S, obtain four matrices A, B, C, D, such that when plugged into this formula, they yield G of S.